Today, let us discuss about multi-loop controller. The multi-loop control means it has more than one measurement, but one manipulation variable. If you consider the conventional controller, there will be only one measurement and one manipulation. That is conventional controller. But in multi-loop controller, more than one measurement, but only one manipulation. That is called cascade control. Split range controller is there. In that case, only one measurement, but more than one manipulation variable. That is called selective control, and split range controller comes under this category. Split range and selective control. These are all comes under this category. Cascade control comes under more than one measurement, but one manipulation variable. That we will see now. If you consider the CSTR, here the feed is fed into that CSTR. It's because of reaction, it will emit heat energy. That's why its temperature will rise. To keep the temperature constant, we have to use the coolant to remove the heat. The coolant will enter here into the jacket, and it will remove, and it will leave from the jacket here. It will enter here and leave here. That's why it take away the heat generated by this exothermic process. So it is a simple controller. Here we want to control T, that temperature of the CSTR. For that, a temperature transmitter is there and temperature controller is there. Set point is given, and the set point for T is given. T set point is given, and T is measured, compared. A conventional controller will regulate the flow rate of coolant. Flow rate of coolant is suppose temperature increases means coolant flow rate will be increased. If temperature decreases means coolant flow rate will be decreased. That is the idea of control. If coolant flow rate is increased, the amount of heat removed will be more. That's why heat will be decreasing. If heat decreasing means we have to reduce the coolant flow rate so that heat will increase. That is the conventional controller. Now we will consider two cases. One is two disturbances. Two disturbances we'll consider. One is increase in TI, that is feed inlet temperature, TI increases. In that case, as TI increases, immediately T will increase. So that will be noticed by this temperature transmitter, and it will be given to temperature controller. Immediately it regulates the coolant flow rate so that T will be controlled. T will be controlled. Another second case is if TCI, inlet temperature of the coolant, that is TC, coolant temperature inlet. Here, coolant temperature outlet. That's outlet. If inlet temperature of the coolant increases, what will happen? The amount of heat removed by the coolant will decrease. Amount of heat removed by the coolant will decrease. If TI increases, T will increase. In turn, the flow rate of coolant will be increased, so that amount of heat removed by the coolant will increase, so that temperature will be controlled. In the first case. Second case, as coolant inlet temperature increases, because of higher temperature, it can remove less amount of heat only. That's why T will increase. T will increase. But in that case, also we are increasing the coolant flow rate that will control T. This is indirect effect. This is indirect effect. This is direct effect. That's why this single loop controller will control this direct effect effectively, but the indirect effect it is difficult than direct control. That's why its effect will be lesser in the case of second case. Suppose if you are able to control this flow rate, whenever coolant flow rate increases, then before it makes any changes in T, we can avoid a change in T. If in the conventional controller, the temperature control directly regulates the flow controller. For both type of disturbances, either in the TI or in the change in TCI, it directly regulates the valve. Instead, the controller can give set point for flow controller. Here, if any change in TCI is measured, coolant temperature is measured here, as well as T, both are measured. Two measurements. T is the primary aim of controlling the CS is we want to control T. We are not interested in TC, but that affects T. That's why we are measuring TC here. That primary controller gives set point to the coolant temperature. Here, TC set point is given by the primary controller. The coolant temperature is measured here. If any deviation is there, based on that, it will regulate the coolant flow rate. You consider the second case. If any change in coolant temperature, that will be found then and there. That is compared with the set point, but there is no change in set point. There is no change in set point given by the primary controller. But the coolant temperature deviates means the second temperature controller, that second temperature controller got some error because of deviation in coolant temperature. That's why it will regulate the valve so that the change in coolant temperature will not affect the process T, process variable T. That is the idea behind the cascade control. That is the primary controller, that is the controller which controls T, does not regulate the valve directly. Instead, it gives set point for coolant temperature. Coolant temperature is measured, compared with the set point. If any deviation is there in the coolant temperature, accordingly, it will regulate the valve. Let us check whether it controls the first case. First case, there is no change in coolant temperature, but because of change in TI, T increases. That's why there will be a change here. That is the process variable 1, that is primary variable, there is a change, but there is no change in set point. That's why you will get an error. Because of the change, the here set point for coolant will be changed. Therefore, in that case also, it will regulate the valve. In both cases, it will regulate the valve. The first case, without affecting T, it regulates. The second case, it will the T will be affected, but immediately it will take action. That is called cascade control. It has two loops. This loop is called inner loop or secondary loop. Inner loop or secondary loop. The first one is called primary loop or outer loop. Outer loop or primary loop. Outer loop or primary loop or dominant loop. Dominant loop. The primary loop gives set point to the secondary loop. Set point to the secondary loop. Actually, secondary loop only manipulates the manipulated variable. First loop only gives set point. that we will see in the block diagram. Here, the process 2 is the flow, the coolant flow control loop. Coolant flow control loop. Process 1 is the exothermic process. T is the primary variable. So the process is divided into two parts. One is the model of coolant temperature, that is TC. Here T, it is separated into two parts. Here we are going to manipulate the coolant flow rate by measuring coolant temperature. You see here the coolant temperature is measured here. Compared with the set point, coolant set point given by the primary controller is compared with the coolant temperature. If any deviation is there, the secondary controller will regulate the flow rate of coolant. The primary controller is the outside. Here the T is measured. T set point is given by the operator. Compared with T, if any deviation is there, the error will be given to the primary controller. That will change the set point of coolant. It doesn't directly regulate the coolant flow rate. But in the conventional controller, we are only measuring T. This is the conventional controller. Conventional controller. We are measuring T directly compared with the T set point. If any deviation is there, it directly regulates the flow rate of coolant. Now, let us consider the example process. Let us consider a third order process, 0.5 S plus 1 and 0.1 S plus 1 and 1 S plus 1. This is a third order system. Third order system. This we want to control means the ultimate gain for this process is 19.8. The ultimate period is 1.125 seconds. That we know. So if you use a conventional controller, what we will do is set point will be given here and the PID controller is employed 1 upon 0.5 S plus 1 and 0.1 S plus 1 and S plus 1 is the process. This is the way by which we will control a conventional controller. Suppose this is separated into two parts. One is process 2. Process 2 is 1 upon 0.1 S plus 1. This is process 2. Let us assume that this is like a coolant flow controller, coolant temperature controller, coolant temperature controller. Another one is primary, that is exothermic process. Its let us assume that its transfer function is 0.5 S plus 1 and S plus 1. This is, we are separating this into two parts, process 1 and process 2. Here, we can implement cascade control to improve the performance here. If you see the time constant of this process 2, that is very much less than the dominant time constant of the process 1. Here, the dominant time constant is 1, not 0.5. The slower one we have to consider, that is 1. This is less than the dominant time constant. That's why we can implement a cascade control. So if you implement a cascade control, what we have to do is first, let us consider this 1 by 0.1 S plus 1, that is a secondary controller, and implement here a P only controller. So this can be controlled because since it is a first order process, here K can be increased to any value, up to infinity can increase. This has to be cascaded to process 1 that is 1 upon 0.5 s plus 1 and s plus 1. This is like T that is measured here. T is, this is like T coolant. You can assume like that. The T is fed back here. One controller will be there. This is a PID, another PID controller. You are comparing this with the T set point. If any deviation is there, that error will be given to the PID controller. It will give TC set point for the coolant. Here we are feeding coolant temperature. This is the idea. By using that, we can implement a cascade control. Now let us compare both methods and check which gives better performance. So let us consider this. Consider the simulation of this in MATLAB. Here the first one is conventional controller. The ultimate gain is 19.8. 19.8 theoretically, but if you put 19.96, it gives unstable response. 19.8 for that, it gives P only. I am implementing P only. I am just implementing P only. It is multiplied by 0. Derivative also multiplied by 0. If you see, it's almost sustained oscillation. If I give, theoretically we got 9.8. Let us give 9.96. For that, it becomes unstable. 9.6. So around 9.8. Yes, its amplitude go on increases. For 9.6, it gives 9.9, it gives sustained oscillation. So the ultimate gain is 19.8. For a PID controller, it should be multiplied by 0.6. The ultimate period is 1.125. This has to be divided by 2. That's why 19.8 multiplied by 0.6 multiplied by 2 divided by 1.125. That is KI. KD is 19.8 multiplied by 0.6 multiplied by 1.125 divided by 8. So that is given. The same we'll give here. 19.8 multiplied by 0.6. Yes, we gave the same. For this, it is given 15, because since it is a first order process, we can give 15. So, yes, for set point change only, let us check. For servo response, let us check. For this conventional controller, IAE is 0.63. For ISE is 0.28. And for cascade control, 0.34 and 0.14. That gives better dynamics. We see the response also. The cascade control has less overshoot and settles quicker. The black one is the conventional controller. It gives better dynamics. Now let us check. This is change in This is identical to change in input. This is identical to change in this is change in coolant temperature. The first this disturbance is change in coolant temperature, identical to coolant temperature. This is final value is 1. If we check identical to coolant temperature. Now we are giving both conventional as well as servo as well as regulatory. Let us check only regulatory. Final value is 0. Now let us check regulatory alone. Regulatory, that too coolant temperature alone. You see that IAE, if you see 0.06, 0.003 ISE for conventional. Here 0.0053. Here 0.6, here 0053. So it gives better dynamics for regulatory response. You see conventional controller large overshoot. For cascade control, it has better dynamics. If you see for this, that is change in TI. Let us check for change in TI. That is inlet temperature of feed. For that, let us check. That has immediate effect in the output. That's why we are giving outside that process. It has immediate effect on the T. That's why it is given here. If you see, for that also, it gives better dynamics. You see here 0.7. You see. In that case, for inlet temperature, change in inlet temperature, change in TI, you consider like that. Both has same amount of overshoot. But settling time, if you consider, cascade control settles better. The overshoot alone is in both cases same. But settling time, if you see, better dynamics. So in both cases, the cascade control gives better dynamics. So that we can see from this simulation. If you consider all together, let us consider all together. That is servo as well as regulatory, and they are both the disturbances. Let us give. What is ISE IA? If you check, if you consider all together, here 1.3 IAE, here 0.7 only. Here 0.57 ISE, here 0.3 only. If we see all together, so in all the three cases, settling time is better. Here, settling time for servo response, settling time is better. For change in coolant temperature, almost insensitive. I mean, insensitive to T. For TI, both has same overshoot, but settling time is better for cascade. That's why cascade control gives better dynamics. As far as stability is concerned, here already we have seen that for 19.8, it gives unstable operation. Sustained oscillation gives for 19.8, almost sustained oscillation gives. Here in cascade control, I want to put 19.8. What happens? Let us check. If you, this is the same process, but cascade control, I am putting 19.8. Let us check. For 19.8, this process becomes unstable. But in cascade control, if you implement, you see the dynamics. Your dynamics, I gave 19.8, even though it is stable. That's why cascade control improves stability also. Cascade control improves stability also. Even I put 19.8, it is still stable. So it improves stability also. It improves stability also. So for this, if I give 19.8, for this, if I give 19.8, it becomes unstable. You see? So for 19.8 with the P only controller, conventional controller exhibits sustained oscillation, whereas cascade control, but both has steady state error, that is different. But cascade control gives better dynamics, even though for the same ultimate gain that you can notice. Here also it exhibits sustained oscillation, but cascade control reject the disturbance that you can notice from this. Where and all we can implement the cascade control. This is heat exchanger. This is heat exchanger. So it is a heat exchanger. Here we are interested in controlling the temperature of stream 2. That's why we are measuring the temperature of stream 2. We have to regulate the flow rate of stream 1. It is a hot water or hot fluid, TH, is used to heat stream 2. If temperature decreases, the flow rate of this stream 1 will be increased. If T increases, this flow rate will be decreased. That is idea. Conventional controller, this primary controller directly regulates the flow rate of this stream 1. Instead, here, the flow rate is measured here and it is controlled by another flow controller. For that flow controller, the primary controller gives set point. That is FH set point is given by the primary controller. T set point is given by the operator. So any change in flow rate is there, then and there it will be controlled by flow controller. That's why change in flow rate will not affect the temperature. That is the idea behind this cascade control. This also controls other disturbances by the primary control. The second one is this is furnace control. Furnace control. In that case, the temperature of this process stream T has to be controlled. T is measured here. Temperature transmitter TT measures the temperature that is given to the temperature controller. Here, to adjust the heat of this furnace, we have to adjust the fuel flow rate. Therefore, the fuel flow rate is controlled by this. This primary controller gives set point for this fuel. Set point is given. Fuel flow rate is measured by this flow transmitter. Both are compared. Fuel flow rate is regulated here. For any change in fuel flow rate, because if the upstream pressure changes, the fuel flow rate will change. In that case, it will be regulated then and there. That's why any change in fuel flow rate will not affect the furnace temperature. For all other disturbances, this primary controller will change the set point of this flow controller. The third one is distillation column. In the distillation column, the boiling point of top product will be lesser than the boiling point of the bottom product. That's why the bottom product will be in liquid state. This will be in vapor state. It taken away and it is condensed by this condenser. So you will get again in the liquid state. This will be fed back to control the temperature of this top product. To control this temperature, this distilled top product will be fed back again. That is called reflux ratio control. For that, the main controller measures the temperature here and it gives set point to this flow controller. So the flow controller is the secondary controller. The set point is given by the primary controller. Based on that, if the temperature increases, it will increase the flow rate. That's why set point will increase. Similarly, if any increase or decrease in flow rate, it will be then and there controlled by that. Therefore, any change in flow rate will not affect the temperature. So here also we can implement the cascade control. The same temperature controller can be implemented by using reboiler also. This is first scheme. The second scheme, the temperature is measured here. That is given set point to flow control of reboiler. Flow control of reboiler, set point to the flow of reboiler. Reboiler set point is given by this primary controller. If any change in flow rate, then and there it will be controlled. For all other disturbances, this set point will be changed. That is the idea behind this cascade control. What is happening here? The temperature is measured here. That will give a set point to that reboiler. Reboiler means the liquid in the bottom will be circulated through this heat exchanger. Reboiler is nothing but a heat exchanger. Already we have seen a heat exchanger. That will change its temperature to the liquid. That is called reboiler. For that reboiler, the steam flow rate is measured here. If any change in flow rate of the reboiler, it will be regulated by this valve by the flow controller. The set point for the flow controller is given by the primary controller. That is scheme 2. So in both ways we can implement cascade control.